So tonight I'll introduce you to the Rust programming language and some functional programming concepts that you can use in it. For tonight, so the plan is that I will start by introducing you the language itself, its syntax, how to declare variables and functions, the basic stuff, and then I'll switch to talk about functional programming concepts in Rust, like traits and generics. I'll also talk about error handling, closures, and iterators. So Rust is a fairly recent programming language. It was developed by Mozilla Research, and its first public release was done in 2010. It is multi-paradigm, it is imperative, concurrent, and functional. Also, it is statically and strongly typed, which means that the type of every variables must be known at compile time, and the compiler will prevent you from using different types together. For instance, you cannot add a floating point numbers with an integers as you can do in C, for instance. You need to use cast, explicit cast. Also, the language is both low level and safe, which is very nice because it allows you to get very good performance, but also avoiding the pitfalls that you get in some other languages like C++. And one of the coolest features of the language, in my opinion, is that it provides automatic memory management, but without a garbage collector, which means that you don't pay a cost at runtime to manage the memory. So it works in this way. The compiler is able to infer where the call to the free function must be done, so where the deallocation function must be called, and it can do that at compile time. So there's no cost at runtime for doing that. And one example of a big project that is written in Rust is the Servo Web Engine, which is also written by Mozilla Research. Here are some strengths of the languages. The language provides zero-cost abstractions, which means that even though the language might feel high-level, it will actually compile to very efficient assembly. One example of that is iterators that I will talk about later. Rust is very good for concurrent programming because it prevents data races statically at compile time. So for instance, if you use a variables in 2 threads and you try to mutate it, it will actually be a compile time error. So you need to use mutex or other kind of synchronization to make the code to compile. Also, Rust is very safe, assuming that you only use the safe part of the language, because there's also an unsafe part. So in the safe part, there's no null pointers, and you cannot use a variable after it was freed or before it was initialized. And also, the variables are immutable by default, which is a good thing because mutation can be a source of bugs. And also, since the compiler is able to infer where to free the memory, there's no memory leaks. Well, all of that is assuming that you only use the safe part of the language. So let's now see how we can write a simple program in Rust. So the code starts to execute in the main function, as in many programming languages. So we declare function by using the fn keyword. Then we have the name of the function, followed by parentheses. And between curly braces, we have the body of the function. Here we call a macro that is called println, and this prints text to the terminal. So we know that it's a macro because there's an exclamation mark here. So if it was a normal function, there will not be an exclamation mark. Any questions so far? Yeah?
Quick question. I'm not familiar really. What is the difference between a macro and a regular function?
Okay, so in a macro, you can actually have some kind of patterns that will generate some code at compile time. So we don't see here a complex example, but the println macro could have other parameters, and in the format string, you could specify that you want to print these parameters. So at compile time, it will generate actually other code that will, for instance, lock the std out so that it doesn't have concurrent access with other threads, and it will print the value to the terminal. So it's actually generating code, while macro is, while a function is actually just some code that will be executed as it was written.
Are these equivalent to templated functions in C++?
Not really. It's a bit similar to the defined macros in C++, but it's safer because well, I don't want to enter into the details, but there is like, you cannot misuse your identifiers like you can use what you can do in C, for instance. So let's see how we declare variables in Rust. We start with the let keyword and then the identifier, followed with an optional column and type, because as I told you, there's type inference in Rust, so we're not bound to specify the type. The compiler is able to know that this constant 42, for instance, is an integer. And in Rust, the integers will be 32-bit signed integer by default. So if you don't specify the type, like on the line 2, it will be the I32 type. And to declare a mutable variable, you need to use the mod keyword, which will allow you to reassign other values to this variable. So by default, variables are immutable. And here is how we declare structures. So we use a struct keyword and a name. And between curly braces, we have the identifiers followed by a column and a type. And we can also declare methods on structures. So we use this syntax with impl and the name of the struct. And between curly braces, we declare the methods of the struct. So we can see it's a method because it has the special parameter self, which is the current instance of the struct. It is similar to this in other object-oriented programming languages. So here we have a method that returns a string, and we use another macro, the format macro, that is a bit similar to println, but instead of printing to the terminal, it will return the formatted string. And we have an ampersand before self because this method takes the current instance by reference, because by default value are moved in Rust. So to use a structure, we just specify the name of the struct, and between curly braces we have the identifiers of the names of the field, and followed by a column and the values. As you can see, the first name, we didn't specify what was the value. It's because there's a shortcut in Rust. If the value is the same as the name of the field, it will actually take this value. And you can see on the last line that we call this method that we just declared by using the usual syntax of a dot and the name of the method with parentheses. We can also use attributes on types that we define. So for instance, here we use the derived clone attribute, which will generate some code that will allow us to clone this value. And let's see what one feature that is common in functional programming languages, pattern matching. So here we match over a number, and in the first two cases, it looks similar to a switch statement in other languages. So we have a value, and on the right side of the fat arrow, we have the body, so it will be executed if it matches the pattern. The third pattern uses an OR, so if the number is either 3 or 4, it will execute the code. And the fourth pattern is a range, and it is an inclusive range. So if the number is from 5 to 10 included, it will print between 10 and 5. And since in Rust, pattern matching must be exhaustive, we must manage all possible cases, but we cannot possibly write all numbers because they're too much. We can just use the wildcard pattern, which is the underscore. So that means that if the number is not between 1 to 10, it will execute this case. We declare a simple list type, which is an enum. In Rust, an enum is a sum type, which means that a variable can either be the empty list or cons, which contains two values, the element of the list followed by the rest of the list. So we can use pattern matching to destructure a value, which means that it will assign the value inside the variant, for instance, to variables. So in this case, we have a SUMList function, and we match over the list. If it is empty, we return 0 because the sum of an empty list is 0. But if there's an element in the list, we match over cons, and we assign the first value to element, and the rest of the list will be assigned to a variable called rest. And the body of the function on the right just sum the element plus the sum of the rest of the list. So, any question? Yeah.
Can Rust and Fart return type?
Oh no, that's a good question. The type inference is only local in Rust, so that means only local variables will get their type inferred. So you have to specify the type of the parameters and the return value, which is not a bad thing, by the way, because it acts as a documentation. Yeah?
Is Rust tail recursive?
Well, since Rust uses LLVM, it does not enforce tail recursion. However, LLVM can optimize it in some case, so you might get it or you might not.
Why did you box the list?
Oh, that's another good question. In Rust, types must have a size that is known. So if I didn't use box and I just use list, the size of the type will not be known, and Rust cannot work with that. So I put the list in a box so that the rest of the list will be allocated on the heap. So since it's just a pointer, we have the size of the whole enum. Yeah?
The ampersand before list, in the case that you're passing a reference?
Yeah, indeed. And we use the star operator to dereference this reference.
So does it matter that you pass it by value or by reference?
Well, actually, in Rust, values will be moved by default, which means that if it was not a reference and you call this function with a list, you could not use the list afterwards. Yeah?
So when you say you're passing by a reference, does that mean it's actually a pointer?
Yeah, behind the scene, yeah. Indeed, raw pointers can only be used in the unsafe part of the language. In the unsafe part, you can use null, but with a reference, you cannot use null. Any other question? There's other syntaxes to do pattern matching. Here is the if-let syntax. So we have a function isEmpty that checks if a list is empty, and we use pattern matching here to check that the list is the empty list variant. So in this case, we return true, otherwise we return false. And we can also use pattern matching in for loops, for instance. So here on the first line, we declare a range from 10 to 20 exclusive. And then we call the enumerate over this range, which will return another iterator that returns elements of a type tuple, which contain the index as the first element of the tuple and the element of the range in the second element of the tuple. So we're actually destructuring the tuple by using this syntax for the for. It's actually the same as the code you see below. So here we don't use pattern matching, but we are actually accessing the fields of the tuple using this indexing syntax with dot and the index, which starts at 0. So in Rust, many constructs are expressions. For instance, if our expressions match our expression. So that means that you can return a value to a variable from an if or a match. So here, if the number is greater than 42, this string greater than 42 will be assigned to text, otherwise the other string will be assigned. So you shall note that there's no semicolon at the end of the block. If there was one, that will actually return another value, which is the empty tuple, also called unit, which is similar to void in C, for instance. So it is very important when you want to return a value that you don't put the semicolon at the end of the block. So let's see how we declare a function with parameters. So we have the parameter inside the parentheses, and it's the identifier, column, and the type. All of that separated by commas. And the return type is specified after the arrow. So here it's a simple function that returns the maximum of 2 numbers. So let's talk about more interesting features. Traits is, if you like fancy terms, what is called ad hoc polymorphism, which allows you to do functional operator overloading. So it's a bit similar to interfaces in object-oriented programming languages, And it's also very similar to type classes in Haskell. So for a trait, you declare a set of methods and or types that must be implemented for the types that implement this trait. And it's also very useful for generic functions, as we'll see later. Here's a bunch of examples of traits from the standard library. The display trait is used to get a string representation of the value that will be shown to the user. And the debug trait gives you a string representation, but like pretty printing, so for debugging purposes. There's also the equal and order traits that are used for accessing the comparison operators. And the add, sub, and mul traits are used for the corresponding operators. I wanted to talk a bit more about the debug trait because it's very important. So here we have a list type that is over points instead of integers, but we use the attribute derive debug. This allows us to use this syntax with the column and the question mark inside the curly braces to produce the debug representation of the value. So on the last line, you see the output of this code. It's not really readable, so let's see how we can improve that. If you just change the, if you just add the pound character between the column and the question mark, you get actually a pretty print representation of this value, so it's way more readable. So it's very easy to have a debug representation of a value in Rust. Yeah?
So if this is not a tree, it just goes on and on and on.
You mean it could be like infinite?
Yeah, if you have a circular...
Okay, I get it. That's a bit more complicated than that in Rust because there's ownership.
So the answer is just you can't do it in Rust?
No, there's way... you could create a graph in Rust by using raw pointers, for instance. But if you just use the safe part of the language, you'd have to use other techniques like having a vector of nodes, and you use the index for your graphs and such. So it's different. It's like you don't have a graph that will have reference to the other elements that can have a reference back. You cannot do that, so you need to use other techniques. There's two rules that must be respected when you use traits in Rust. The first one is that you must import a trait before you can use methods on this trait. So this is to avoid conflicts, for instance, when you have two traits that has the same methods. And also, if you want to implement a trait on a type, you must either define the type or the trait in your own crate. In Rust, a crate is a project, so it can be either a library or a binary project. So let's see how we declare a trait in Rust. Here we have a trait read that has a single method read that takes a string and returns a value of the type self. Self is the type that refers to the type on which you implement the trait. And after that, we implement the read trait for 32-bit integers. So we declare the function and its body, and in the body we just call parse, which is a method from the standard library. So that's as simple as that. Let's see a more complex example. Here we have a trait equal. But as you can see here, the not equal method has a body. This is the default implementation. So that means that when you will implement this trait, you only need to provide the function equal. You're not bound to declare also the not equal function. So if you don't, it will use this default implementation. In the second example, the order trait, we use the column equal, which means that when you want to implement the order trait on your type, it must also implement the equal trait on this type. Okay, let's move on to another topic. Yeah?
We didn't see how these are used. How is read used for an integer?
Okay, you could just call, for instance, well, here it's a bit special because it's an associated function instead of a method because it doesn't take self as a parameter. So you will do read column column read, which is the name of the method, and a string, and you'll get a an integer as a result.
But I presume I can have reads for F32, F64, and all sorts of other gorgonzola and cheeses and so on and so forth. So how would I be using this for an specifically for I32?
Okay, I'll show some syntax later, but you could also specify the type when you declare variable, or the type inference can.
So I could say let I colon I32 read some string.
Yeah.
Okay, thank you.
I'll show some other syntaxes later. Okay, and generics allows you to create generic functions and types. It's a good way to avoid code duplication. For instance, if you have a function that returns a maximum of 2 values, you don't want to define it for integers, floating point numbers, characters. With generics, you can just declare it once, and you'll be able to use it on every type. And it uses static dispatch by default, which means that for our maximum function that is generic, if you call it on string and integers, it will actually produce 2 versions of the code in the final binary, which means it will be a bit more efficient at the cost of a bigger binary at the end. So let's try to create a generic function as you will do in C++, for instance. So here we have a function min that takes a generic parameter t, and we have 2 parameters of this type t, and it also returns the same type. So if we try to compile that, the compiler won't accept it. It's because it doesn't know if we can call this operator over the type t. We must specify it somehow. So let's see how we can do that. So we can do that by adding a trait bound. So after the generic type t, we add a column and the trait that must be implemented on this type. So only the types that implement this trait can be used as a parameter for this function. So this code compile. We can also create generic type. So here we have our list type that is generic over a type t. So its element is of a type t in the cons variant, and it also has the rest of the list, which is also of type t. We can also add trait bounds on the generic parameter here. So we have the t followed by a column and the trait. And there's an alternative syntax for that, which is using the word clause, as you can see on the last example. It's actually the same as the other syntax from the second example. Yeah?
With the where clause, I imagine you can apply 2 traits.
Well, in both cases you can, because if you want to implement 2 traits, you must use the plus between them. So in both cases, you could do that. It's just that the word clause might be more readable when you have a lot of generic parameters and trait bounds. So let's see the syntax to specify the type that must be used in the generic context. So on the first line, we're creating a list of U8. So we use this column lesser than type greater than type. It is called a turbo fish operator because some people think it looks like a fish. And on the second line, we use another way. So it is using the column list U8 after the variable name. And the third case is a bit different. We have our tail variable, which is then used afterward with a list that contains a 42 U8. That means that this integer will be of the type U8, which means an unsigned integer of 8 bits. So because we use the variable tail afterwards with a list of U8, the compiler is able to infer that this tail will be a list of U8. Okay, let's talk about error handling in Rust. We have the option type to encode the absence of value and the result type to encode the error in the type itself. We'll also see some macros, and as I told you, there's no null in Rust, so if you want to simulate that, you can use the option type, and there's no exceptions in Rust. So the option type is declared, as you can see here, with an enum. It has a variant sum with a value of type t, and also a variant none. So when you have no value, it will be none. It is similar to the maybe type in Haskell. So when you use this type, you cannot access the value directly. You either need to pattern match over the value, so that if it is the sum variant, you can get a value inside, or you can use some other methods that I'll show you later. Yeah?
What's the type of num? It's just...
Well, num is of type option T.
Right. Which T?
Okay, well, you could specify the type using the turbofish operator. So you could write none, column, column, lesser than the type, and greater than. So it will be like, if you need an option of a U8, for instance, you'd write that. So there, as you can see, some use the type T. It's like if you had a function that takes a parameter T, but none takes no such parameter. But since it is of the type option T, you still need to specify it if the compiler cannot infer it. So let's see a simple example. Here we have a vector, and we call the first method over it. But a vector could be empty, so it returns an option. Here we use pattern matching, and on the first case, we have the value that is wrapped inside sum. And if we get a value, we just add 1 to it. And if there's no value, we get none. So it executes the second case, which just returns 0. There's many methods that you can use on the option type. I'll just show you some of them. The first one is unwrap OR. So it will try to get the value inside the option if there's one, but if there's no value, it will return the one you specified as a parameter. There's also unwrap or default, which is similar, but instead of returning a parameter, it will return the default value. The default value is known because there's a trait called default, and this trait is implemented on most of the types of the standard library, and you could also implement this type, this trait on a type of your own. Map is another method that takes a function or a closure as a parameter, and it will apply this function on the value if there's one, but if there's no value, nothing will be done. Map OR is kind of the combination of map and unwrap OR. So it will call the function if there's a value, or return the value if the value that you specify as the first parameter if there's no value. So and then is another method that also takes a function as a parameter, but this function returns another option. So it will call this method if there's a value inside it, and if it returns sum, it will flatten the option, so you only get one sum, so there won't be nested sum value, for instance. And also another important method is the clone method that will clone the value inside the option. It is mainly useful when you have an option of a reference, which means that if you have an option reference to integer, when you call clone, you'll actually get an option over an integer, so the reference is gone. So this is assuming that the type inside the option is, you can clone it, so it must implement the trait clone. So the result type will encode the error in the type itself. It is defined, as you can see here, it has an OK variant that contains the value itself, and another variant that contains the error. It is defined with the must use attribute, which means that you get a warning if you don't use a result, which is kind of nice because you want to handle errors and you want to know when you don't handle them. But since it's just a warning, you can just ignore it because who cares about errors anyway? It is very similar to the iter type in Haskell, and it provides many methods that are similar to the one I just showed you for the option type. Here we have an example. We call the parse function method over a string, and we specify that we want an i32 back. So this function can fail, so it returns a result. So here we have a pattern match over this, and if it is okay, if we were able to parse the value, we just print the value, but if there was an error, we print this error. There's the question mark operator that is very useful when we work with result type. So it will allow you to get a value inside the result if there's one, but if there's an error, it will return the error from the function. So it is a shortcut for pattern matching, Like if there's sum, you get a value. If there's error, you return a value. I will show you later the difference between the two. So it's very useful when you handle multiple result types, especially when their error type is different, because it will also convert the error to the one required by the function. So here we have an example of a function SumString that takes two strings as parameters and return a result of an iter32 and can be a parse int error. So in the first line of the body of the function, we call parse, and we use the question mark to indicate that if it fails, return the error from the function. And we use the same for the second line, and then we return OK with the sum of the two values. It is actually the same as if you will have written this more verbose version. So here we use pattern matching, and we get a value if there's one. If there's an error, we return it. Yeah?
When you say return, some string returns, is that correct?
Yeah.
What about the semicolon?
So sometimes you need them, sometimes you don't.
Yeah, when you don't want, when you don't use the semicolon at the end, it's because you return a value from a function, for instance. So here we don't put the semicolon because we return this value. If it had a semicolon here, it will return the empty tuple, as I told you before.
So would it be right to say that state missing semicolon and expression's done?
Yeah, exactly. Yeah.
But you said that question mark will return the value, and you still have semicolon.
Well, it used an early return behind the scene, and for that, well, it's kind of replacing the code at the top by the code at the bottom, and you can see that we still use a semicolon here, even though we have an early return here. Yes?
This question mark operator looks really convenient. Is it part of a trait?
There is a trait called try that is only implemented for result for now, but it will be added for the option type also in the future. So I believe you could also implement this trait try for your own types. As I told you, there's no exceptions in Rust, but don't panic. There's something similar that you could use.
It's all right.
So it's called panic. So panic is a macro that you can call that will either unwind the stack or abort. By default, it will unwind the stack, and you can specify in the configuration if you want to abort instead. So unwinding the stack means that everything will be cleaned up, the constructors will be called, and the memory will be freed and such. So when you use abort, nothing of that is done. Well, it's the OS that will do it, but yeah, it's different. So here we have an example where we call parse, and we check if it's an error. If it is the case, we panic. And as you can see with panics, we can also use this formatting string syntax with arguments. Any question? Yeah.
Is it possible to catch a panic?
Well, we cannot catch the panic itself. We cannot catch the unwinding, which means that you should not rely on that for doing something similar to exceptions. So because if you change the configuration to use abort, it won't be catch. So there's a bunch of other macros that will panic. There's unimplemented that you can use for some code that is not written yet. Also unreachable. It is very useful when you have some code that should not be reached, obviously. So for instance, if you generate a random number from 1 to 10 and then you pattern match over all these numbers, but you still need to have a wildcard, well, you could use this unreachable in the wildcard because it will indicate a bug if you reach it. There's also a few assert macros, and they have a debug variance, which means that you can also call debug assert equal, or debug assert not equal. The debug variants are only executed in debug mode. So in release mode, it won't be executed. That can be useful if you have some hot code path that must be very efficient when it's in release mode.
So what about unreachable? You have a code that will not be reached? and you mark it with that word.
Yeah.
And if it's reached, then what?
It panics.
How is it useful?
Okay, so well, it's when you have a bug, you want to know it as early as possible. So you just panic so that the application aborts with a message. It's like when you use some asserts in your C code that you want to ensure some property, similar to that you have like runtime check to make sure that everything is okay. And when you panic, you get this message with the first 2 lines. But if you want to see the stack trace, you can set the environment variable Rust backtrace to 1, which will show you the code path that were taken in the execution that leads to the panic. So it's very useful for debugging.
Does that mean all the debug tables are in the binary?
Well, in this case, it was compiled in debug mode, so you have access to the line numbers. But if it was compiled in release mode without debug symbols, you will not get the line numbers. But indeed, here you have more data in your binary, so that's why there's features to remove that to get a smaller binary, and you won't get these beautiful things. Let's now talk about closures. So a closure is an anonymous function that can access the variables from outside the function. In Rust, normal functions cannot access the environment, so that's why we have closure. And contrary to normal function, we have type inference with closures, which means that we don't need to specify the type of the parameters or the return value. And by default, closures are located on the stack. So let's see an example. Here we have an optional value, and we call the map method. And instead of just providing a function, we use it closures. So between the 2 pipes, we have the parameter num, and we have, after that, the body of the closure would just return num plus 1. And the second example, we have our SumString function, but we use some combinators like indent, which requires a closure. And here we decided to specify the type of the argument and the type of the return value, even though we use the underscore in the result type to specify that the compiler must infer this part of the type. So here, since we have multiple statements, we need to use curly braces. Because as you can see on the first line, we didn't need curly braces because there was only an expression. So in functional programming languages, we like to pass functions to other functions. So let's see how we can do that in Rust. Here we'll declare a functor trait with a method called fmap because we did the same mistakes as in Haskell. And we have a func parameter which is of type f, which is a generate parameter. And we specified in a word clause that this f generate parameter must implement the trait fn, which takes a self and as a reference and returns the generic type O. And it is not shown here, but this trait was implemented on the integer, for instance, so that we can call the fmap method over the integer on the last line. And here we have a closure that captures the variable 2 that is declared right before. Any question?
I don't have a question, but I have an objection.
Well, this is different than in Haskell actually because Rust doesn't provide hierarchy type yet.
Do you need to import fmap as well?
Yeah. This code is not complete. There's the implementation over the integer that is not shown in the import. And here we can see how we can return a closure or a function from another function. So here we have a function called compose that has a few generic parameters. And it takes 2 functions as a parameter, but using the word clause, we specify the traits that must be implemented. And the return value is using this special syntax with impl and the trait. It is an unstable syntax, by the way, so it's only available on the nightly version of Rust. So what this syntax means is that the return value must implement this trait, and the compiler will figure out what is the actual type. So in the body of the function, we have a closure that calls the toFunction that we got as a parameter. And we also specify the move keyword before, because we want to specify that these values will be moved into the closure. Because for closure, it's different. The values won't be moved by default. There's also another way to return a closure which use only stable Rust, which is to box the trait, so it returns a heap allocated value instead. So this one don't allocate on the heap. Yeah?
Will this compile here without the move keyword?
No, because of some lifetime issue that I don't want to talk about. So the last feature that I want to talk about is the iterator. So it allows you to manipulate some kind of collection and range, and it's very high level, which means that you have some methods like filter and map that you might be used to, but it's also zero cost in most cases, which means that even though you use some high level fill, the generated code will be very efficient assembly in the end. Iterators are used for loops. And what is very nice is that by using iterators, you can have some code that does not require mutation, as we'll see later. And iterator is actually a trait. So let's see an example. Here on the first line, we have a byte string. It is different than a normal string because strings in Rust are a Unicode string. So here we just specify with a B before the literal that it is a byte string. So it's not a Unicode string. And then on the third line, we call iter to get an iterator over the bytes of the string. And then we use a bunch of methods in it. So we first call map, which takes the value, well, one value from the iterator at a time, and we call the closure. So here we just convert the byte to its uppercase representation. Then after that, we call take while, which will return as many elements as this closure returns true. So here we have a parameter byte that is preceded by an ampersand, which means that we use pattern matching to get the value from inside the reference. And we check that this byte is different than the pipe byte. Yeah?
So you are defining a new variable named string. Just like the first one is named.
Yeah.
I presume that the shadow is it.
Yeah, indeed.
The first one, is this a common idiom?
Yeah, that's a common idiom, yeah. Yes?
So earlier when we passed by reference, we had to like dereference when we did the match.
Yeah.
And I don't see that happening.
Yeah, indeed. It's because we could have used the dereference operator, but here instead we use pattern matching by putting an ampersand before the byte. So it's actually kind of if you have a reference and you pattern match to get a value inside it. So after the take while, we call again map to convert the byte as a Unicode character, and then we filter it to only get the alphanumeric character, and then we collect it into a string. We had to specify that it wasn't a string on the line 2 because it could be collected in something else like a vector of characters. So let's see another example of using iterators. So here we have our byte string, and we call again iter over it. And then we zip it with an infinite range, so from 0 to infinity. And we skip the first 5 elements in the iterator. And again, we use pattern matching in the for to get a character and its index. By the way, it's similar to calling enumerate. And in the body of the for, we have a condition, and we just print this character. So it will actually print the character from 5 to 19. Yes?
3 dots is inclusive, and 2 dots is not inclusive?
3 dots is inclusive, and 2 dots is exclusive.
Does this include 0 as well?
0 is included.
Okay.
Yes?
What's your exit clause on there? Is it just going to be forever? Is the if tied into your for?
Well, since zip will take only, and it will position an iterator with the smallest amount of value, which is, in this case, the string. It will stop at the length of the string and not going to infinity. So I wanted to take this opportunity to tell you that I started to write a book about Rust a couple of months ago. So it is called Rust Programming by Example, and the editor is PactPub. I read this book with one of my friends that is called Guillaume Gomez, which is a contributor to the Rust compiler itself. So if you're interested, this book is a by example series, which means that you will learn the language by doing some projects. Even though you need some experience in other languages, you don't need to know Rust itself to read this book. So the first project will be to create a game, a Tetris game that is implemented with the SDL bindings. The second project is a MP3 player with a graphical user interface that is written with GDK. And the last project is a FTP server that will be written with Tokyo, which is the asynchronous library that is used in Rust.